is X-ray production and interactions with matter. And the first two are the X-ray production target interactions, and they are going to be characteristic of tungsten. The first one is Bremsstrahlung interaction, which makes up about 85% of the primary beam. And that is German for breaking or slowing. It occurs only when the incident electron interacts with the force field of the nucleus, which is in here. Approaching the force field, the incoming electron loses energy, changes direction, and the energy loss is emitted as an X-ray photon. 69.5 keV is the minimum incident electron energy required to produce Brems interactions. Photons produced will equal the difference between the entering and exiting kinetic energy of the electron. And the second interaction for X-ray production makes up about 15% of the primary beam, and that's the characteristic interaction of tungsten. It only occurs when incident electron interacts with the inner shell electron. Immediately an electron from an outer shell, higher energy state, drops in to fill the hole. So it could be from either maybe the L, it can go L to K, or an outer one, so it'd be a higher energy photon released. And then the next five are the X-ray interactions with matter, which would be like the patient. The first one might be kind of hard to see. The top three up here is the photoelectric absorption, and we have the nucleus, and the incident photon ejects an inner shell, K-shell electron out. That becomes the photoelectron, and now there's a K-shell vacancy, so there's going to be a cascade effect with the L shell dropping in to fill the K-shell, and when that takes place, there's going to be another X-ray photon, and then M to L, another X-ray photon. And then Compton scatter, that is going to be the most significant to the rad-tech, and I guess better for the patient, but not good. That's when the incident photon interacts with an outer shell electron and ejects it. The ejected electron becomes the recoil electron, and then the scattered photon comes out, and that's dependent on, I guess, the angle of scatter. So as the angle increases, so if the angle's this way or comes back more, the scattered photon is going to have less energy than if the scattered photon came out this direction. The forward direction would have more energy, so like 90-degree angle is best for us to stand or back more. Coherent scatter is not of diagnostic significance. That's when the incoming incident electron interacts with the whole atom and basically just kind of vibrates it. No ionization takes place. Pair production, it happens directly with the nucleus. The incident photon has to be a high energy incident electron, 1.02 mega electron volts, interacts with the nucleus. A negatron is produced, positron is produced, and the positron interacts with the free electron, and then that discharges again. The matter becomes energy with equal 0.51 mega electron volts from both of those. And photo disintegration. So when the incident photon of 10 mega electron volts or more interacts with the nucleus and nuclear fragments are produced. And neither of these two are within diagnostic range. The most significant is going to be